Swayam Prabha. Digital India. Educated India.
So it's a pleasure to be in Puducherry, very nice city, and so we have lots of beautiful places, and I'm very happy to welcome all of you, particularly our speakers from abroad. When some of you might be coming first time here, it's a very beautiful city. So happy 75th birthday, but in advance, because I was told that he's still not 75. If I'm right? Am I right? Yes. So this is in advance honor to Professor Satyamurthy, and thanks to Laudaraj, Ashwini, Sanjay, and all others who have organized this conference in honor of Professor Satyamurthy. It is really a pleasure, and I hope I will have more time in the evening to talk about him, my personal interactions. But I should just quickly say that he has been a great friend and a guide and a scholar with humility, which is very rare to find these days. So many of you know him personally. He has been a great scholar. His main journey has been, of course, at IIT Kanpur to IISER Mohali, and then, of course, he has been invited in several places at adjunct positions and so on. But I think IIT Kanpur and IISER Mohali are the two places where his heart belongs. So we will talk more about Professor Satyamurthy, but it's a great time to honor him. He's really a great scholar. And most importantly, when I grew up doing PhD, he was one of the young faculties, along with few others like Professor Gadre, Professor Jemmis, who are all here, to whom we'll look up to during my PhD, because they are not too senior to me. So they were kind of in a touching but slightly larger distance than touching. And I could never touch them, but they are still in a touching distance. So thanks really for this conference. Before I start, I must also announce that next week at this time, which is 8th of November, and Sunday, I'm actually conducting an NPTEL Plus workshop. Many of you may know, of course, NPTEL, but NPTEL Plus is a separate platform which has focused workshop. This is 10 hours workshop, 5 hours on 8th, 5 hours on 9th, and this time it is on DFT in computational chemistry. So mainly for the students. So the registration will close, I think, sometime middle of this week. So those who are still interested can register for this course. So there will be a lot of hands-on session and also the little bit of theory of DFT. So just a small announcement before I come to my talk. And this is very special in year of 100 years of quantum mechanics. I know Sushant is always excited about quantum mechanics. So the physicists have been excited, and this year's Nobel Prize in Physics is very significant because for the first time there is a clue that maybe quantum mechanics is applicable to macroscopic system. And I think that would really change a lot of things. Though I believe the Nobel Prize was more in honor of the 100 years of quantum mechanics, that they looked at this particular work in a very deep manner. But as you know, it's a game-changing science. It has a new paradigm, disruptive thought. It has a probabilistic description instead of classical certainty. And today, the quantum mechanics is not just a figment of theoreticians' imagination, but it is being able to generate quantum technology, quantum computing, quantum materials. And I think even from the government side, there has been a lot of there's a lot of emphasis on some of these topics. However, could this have been predicted by a computer system from any existing rules, pre-existing rules at that time? Could AI and ML have discovered quantum mechanics? I think that's a provocative question. I don't think so, but many might think that the AI and ML could have discovered. So if you go back in the 1900s, the rules that existed would not have been able to even predict quantum mechanics. So I think with that, I would specifically say that the quantum mechanics applies to this region, and I always love to say that quantum mechanics is more applicable to chemistry than any other subjects. Because if you look at the length scale of the chemistry molecules in chemistry, they fall right in the quantum mechanics. Whereas in biology can be slightly outside. Of course, bulk materials, physicists deal with many types of materials. Some of them you don't need quantum mechanics. But chemistry is all about quantum mechanics. And unfortunately, in chemistry, quantum mechanics is neglected. I think that is, again, a feeling. Many of you may or may not agree. Chemistry is not just synthesis. It has all understanding from quantum mechanics. So you can see this multi-scale hierarchy where you have molecular dynamics, mesoscale, continuum scale. But you can see the QM scale are in the length scale where the molecules or even slightly larger molecules belong to. So it's a very important thing to understand how much of classical simulation do we need. Today, a lot of people are doing classical simulations for many problems, but how much of it we need? And this is why this Nobel Prize in Physics is very relevant today, as all of you know. QM is, of course, expensive, but would quantum mechanics solve its own problems through itself by developing quantum computers? So maybe when the quantum computers come, it can do much larger problems, and probably we need less and less of classical simulation. I'm going to talk explicitly on what is on the left side of this, of the relativistic coupled cluster, but we are developing a lot of formalism, as you can see on the right side, which are for resonance and decay, using complex absorbing potential, and of course more technical things on the left side, where we are developing relativistic coupled cluster. So lots of recent works are there. I will not go into the details of each of my work, but let me quickly say that the non-relativistic quantum chemistry within the BIO approximation is very well developed. And coupled cluster, which is a gold standard of quantum chemistry, has been applied, both single and multi-reference versus. There's a very high precision, however, required for the heavy atoms, which requires relativistic effects. So combination of the two, it seems it's easy, but it has not been very easy. So combining relativistic effects has not been very easy because of very fine terms of the relativity. And what we have done is take a simple Dirac-Coulomb Hamiltonian and then looked at the Dirac-Hartree-Fock and then looked at the coupled cluster as a method for correlation, which actually brings in the best of both. And we have yet to address many other effects like QED, bright effects, and so on. Ground will automatically come within the bright, but those are something that are happening, and we believe they are should be better taken care by perturbative methods rather than taking it within the Hartree-Fock. It's easier to take them within by doing an extra perturbation approach apart from the coupled cluster. So there's a very nice article by Trond Sai this year. It says, does chemistry need more physics? It's a very interesting article. For those have not seen the article, I request them. Trond Sai is one of the leaders of the relativistic quantum chemistry. So he says, of course, you can see what would happen if without relativity and so on. So inclusion of relativity is very necessary for correct description of structure, bonding, and properties of heavy elements and their compounds. Very recently, I wrote a review on this particular book, which I myself have edited. It's a Springer Nature book on theoretical methods, algorithms, and applications of quantum systems in chemistry, physics, and biology. So this is the Dirac-Coulomb Hamiltonian. It's a 4-component Dirac-Coulomb Hamiltonian, which is what has been used quite clearly. Of course, lots of effects are still missing. The bright is one of the things that is missing. With this, we do a standard Dirac-Hartree-Fock method, and then on top of that, we use coupled cluster theory. So the orbitals, of course, change. Instead of normal spin orbitals, now they have the spinors. So using those spinors, you can redesign the coupled cluster. But you have to understand that the integrals with the spinors and with the normal spin orbitals are quite different. The symmetries are quite different. So in programming, there is a lot of effort that has to be done, very different effort, and a lot of my students who did that. Very quickly, that's the coupled cluster, as many of you know. It's an exponential function with singles, doubles, And we have also done approximate triples with single reference as well as multi-reference theory. Multi-reference theory, I'm not going to speak, but my student Suhita is there, who also worked on multi-reference theory. The triples, low order triples. But we are normally going to look at the single reference theory. So this is the couple cluster. As you can see, it has the reference wave function psi 0. Then you can have a single excitation, double excitation, triple excitation. But important thing here is that they come within the exponential. So lot of effects which are products of this excitation, which come in a very effortless manner. And these are the working equations, which is very important to realize that they have a Campbell-Baker-Hausdorff expansion when you do a standard similarity transformation, and that makes it size extensive. However, our interest was from the beginning to do a Hermitian expectation value. Hermitian, as you can see, the functional there is not Hermitian. So we had looked at a lot of ways to do Hermitian, because for properties this is very useful. And when you looked at the relativistic first order property, we tried to look back, how will they give in the Dirac-Hartree-Fock method? The trouble there is that the T dagger is not minus T. So this is not unitary. And hence the norm does not get cancelled. So that's the real problem of the couple cluster, because T is only a whole particle excitation. So it is not, it cannot be cast exponential. T is not a unitary operator. So what we showed was that, however, the norm can be cancelled by a disconnected part of the numerator, and you can only get a connected part of the numerator. So that makes it very easy, because now you do not have the denominator and you have only connected part of the terms. So with that, you can actually look at the properties. And a very simple way to look at those properties is just to get average value. But the problem with this, however, is that although you now have only connected term, because of the fact that on the left you have a T adjoint and on the right you have a T, the series builds up. So it basically becomes an infinite series. So there is no natural truncation even for the first order property. The second problem is that the Hellman-Feynman theorem is not obvious, because of the fact that the T's are not obtained variationally. As all of you know, if I have a variational theorem, you have a Hellman-Feynman automatically built in, but here it is not so. So that was not very clear. However, later, a lot of people, in fact, Jorgensen, Bartlett's group, several groups, we also did for the properties, tried to look at a stationary functional of this kind, where they bring in a new de-excitation amplitude lambda, and with that, they multiply this exponential minus th exponential t, and then do a variation with the t as well as with respect to lambda. This is a very clever way of doing. It's called the Lagrange variation or constraint variation. And you can clearly see when you do a stationarity with respect to lambda, you get back the original couple cluster equation, which is similarity transform. And when you do with variation with t, you have a coupled equation between lambda and t, but there is already a partial decoupling because the t equation comes out easily. So just get the lambda from the second equation, and now it's a stationary thing. So I can, instead of H, I can put my dipole operator, and it will have the Hellman-Feynman theorem. The question is, the first part, which is a very natural way of looking at the first order property, and the second part, do they give same results? That's a very interesting point to notice, because the first part has a non-terminating series. The second part terminates automatically. It's stationary, it has a Hellman-Feynman theorem. So that's a lot of good thing there. So that's what I have written down here clearly. So these are the variations that we do. Unfortunately, they don't give identical results. Then people looked at a properly Hermitian couple cluster. So how do you do that? You actually do an exponential minus sigma, which is unitary. How do you make unitary? If T is only a whole particle excitation operator, you subtract from T adjoint, which is a de-excitation operator. Then this sigma becomes anti-Hermitian, and very quickly you can see that the exponential sigma becomes unitary, But then we found out that the Becker-Hausdorff expansion, it is still a non-terminating series. So the series is basically same as the average value series. So although we tried Hermitian coupled cluster, and that's one of the message that you cannot have a Hermitian functional and a truncating series. That's a message that I have got. You have to lose hermiticity somewhere. In fact, with that you can do the calculations, but it is still same as the expectation value. I tried long back actually using this unitary wave function very early in 1984. I think around the same time, Werner Kutzelnig and a few others were actually working on unitary coupled cluster method. So these are some of the things that I have discussed. One is an average value. I did a lot of work there. And then the Z vector method. However, one interesting, one interesting method that came up, I have written in between, which is an extended coupled cluster, which I will show you is of course not Hermitian, it's a non-Hermitian, but the additional set of d excitation amplitude which came in the Z vector as 1 plus lambda comes with an exponential, and it becomes of course fully extensive, and you can have a truncating series. So it has but it still is not Hermitian. That is very important. I am yet to find a series which is Hermitian and truncating. And that's a very big problem in the context of the coupled cluster. So I will quickly talk about this. I have already said, and this is how you get the operators, first order properties. We'll show some results. So I will not get into that details. So what I'm trying to say is that I then worked with I will skip all this. I directly come to the extended coupled cluster method. So this is a very different kind of method, which was first done by Jouko Arponen, again a very classic paper in Annals of Physics in 1983, and then later Ray Bishop and Jouko Arponen worked on this. This is a very classic functional where you write the average value not like the expectation value. As you can see, you have a lead vector T prime, but that T prime is not T dagger. It's, however, a d excitation amplitude, and what could be shown is by a transformation that you can actually is the final result that we get by a transformation from T and T double prime. I get S and T, new amplitude S. But interestingly, this operator is now connected to right T, and the left T is either connected to this operator A or to two different T vertices. That is what is meant by double linking. And that ensures that when you do a stationarity of this average value, the series remains connected. This is a little bit technical thing, but those who look at the diagrams will immediately understand that this double linking makes it completely connected. And that is a very interesting series because now I can go beyond 1 plus lambda. Please note that if I do a linearized 1 plus S, this will actually become my Z vector method. The 1 plus lambda that I talked about. But because of the fact that it is exponential, I can go much beyond, and I can make it more and more accurate by taking more and more terms. So then you differentiate, you make it stationary with the standard way of energy with S and T. We did a lot of work again on this and lots of truncation scheme. And then we can look at the operator. Well, now it's a Hellman-Feynman theorem is there because it's an average value. So simply put in place of H, the dipole operator, you get the first order property. So that's easy with the Hellman-Feynman theorem. So this is a small comparison of seemingly different theories, but there is a lot of interesting connection like Z vector with the linearized extended coupled cluster, constraint variation, they all are very similar, but the average value is something different. It has a non-terminating series. So that's one thing that the average value stands out against all these. With all these, we actually looked at the dipole moment, and we were trying to understand the relativistic effects by 4-component Dirac-Hartree-Fock method, as I told you, and the correlation by the coupled cluster. So that was the idea for the heavy atom. So as I repeat, the Hamiltonian that we have used is a Dirac-Coulomb Hamiltonian. And with this, we did Z vector. The rest of the part is more technical, except to say that the orbitals are now spinors, which are coming from the Dirac-Hartree-Fock calculations. and not the standard orbital. So with that, we can actually start calculating through the z vector, where you can see you have only a linear part of this lambda. And the same thing will, expectation value will become exponential. So, and we can now separate the electronic contribution, nuclear contribution, and various effects we can see. I will try to show that in the result. So this is the linear expectation value, where I have simply linearized this part. So these are all approximations that one can do. You can see that although it's a non-terminating series, I have simply truncated this at 1 plus t dagger. So that is what I mean by linearized. So the left thing, I have not taken exponential because it's a non-terminating series, as I told you, but I can make approximation by linearization. So some interesting results with a dial basis set for calcium fluoride, strontium fluoride, beryllium fluoride. These are easy to calculate, simple diatomic. We are looking at polyatomics now. And we can look at the average error in Debye with all these methods. So there are different levels of methods, but I think what is instructive is to look at the outcome is that if you simply do Dirac-Hartree-Fock calculation without coupled cluster, there is still a large error. Correlation contribution becomes more and more important, and Z vector incidentally gives smaller error than the linearized expectation value, both double zeta and triple zeta levels. So linearized is somewhat better than Z vector. Correlation of inner core electrons has a very small influence on the dipole moments. So, and the higher energy virtual functions and the relativistic effects do not affect this particular property. Higher order effects, which means you don't need to take bright and so on, but the Dirac Coulomb is of course very important. We also looked at a few others, first order property apart from dipole. Dipole is one, but we looked at this particular quantity called EEDM, electron interaction Hamiltonian, with PT odd parameter, which actually gives you PT odd parameter. And once again, we had results. I just want to try to get you the results. Strontium hydride and strontium fluoride. So you can look at the perpendicular and parallel component, and the deviation is typically within 10%. I must tell here that these results are not very easy to give, because these are very, very sensitive calculations. So of course, the basis set is also another effect. Our basis set is good, but not so good. And I think that is very important to see that there is still an error with the experimental deviation. There's a lot of deviation. And of course, deviation, as you expect, decreases with increasing quality. Then we looked at with increasing basis set. Nuclear magnetic quadrupole moment, that's also another property. And we have just given you the expression for that. Magnetic hyperfine structure calculation. So many of these calculations now we can do for heavy atom molecules using these theories. So these are the PT odd parameters, again strontium halide, strontium hydride and strontium fluoride. These have been our hobby molecules. So you can see now we have done with extended coupled cluster, and in general we find that the extended coupled cluster tends to give better results of this. But and we also compared between SRH and SRF, that the SRH is larger in magnitude than those of SRF. But there are several things that has to be done. This has been published in the recent Journal of Chemical Theory and Computation in this year, so some of these results. Then calcium, some other molecules, again extended coupled cluster, Z vector, and linearized extended coupled cluster. So you can see they're good, and additional correlation terms tend to decrease the property values and make it actually closer to the experiment. I think all that is expected, but what is important is that both the effects have to be taken properly. It is not one versus the other, because otherwise they will be completely unbalanced. It is very difficult to show, of course, for the first order property, any variation method. That you do this, you do next, it will go on decreasing, it will slowly approach the exact value. That is not possible to do, unlike in the case of energy. So that is interesting. So let me probably try to close with this. We have looked at the various relativistic Hamiltonians. The Dirac Coulomb is what we have done. There are calculations in the literature with the Gaunt interaction. Incidentally, I must also say that ours is a 4-component calculation. There are exact two-component calculation, which are also given here, and the non-relativistic limit results, where you don't take the relativity. Then you can see quite clearly the results are very poor. If you take the non-relativistic limit results, they are much poorer. And then these are more technical things, the cutoffs of the various spinors is just like taking this. So let me close with, with the future scope. Of course, the future scope is you have to take bright QED effects for many, many properties as you go ahead, and we plan to take this by perturbative calculation. In addition to diatomic molecules, we need to look at polyatomic molecular candidates for EDM experiments like strontium hydroxide, beryllium hydroxide, and so on. Triples correction, as I said, we have done for both single reference CCSDT, for multi-reference, as I mentioned. They would be very important, at least for the single reference we can do kind of approximate triples correction, which actually was started by Krishnan long back with T3 CCSDT kind of calculation. They can be actually included in the relativistic calculation as well. So I think, yeah. So finally, the non-adiabatic effects within relativistic theory. That is completely, I'm yet to even think of that. That must be very difficult using that will be a grand war. And also to add cap for the decay. So then I can do decay and resonance for heavy atom molecules, which means cap, relativity, couple cluster. And if you can add non-adiabatic dynamics to that, that will be a kind of glorious box of methods, which will be very, very challenging. So with that, so this is what I wanted to say about Raghavachary's work, who did the non-perturbative triples correction long back. These are my co-workers, Kaushik Talukdar, who is now in NIT Meghalaya. In fact, he has been organizing a conference just at this time. I gave a talk on Thursday online. My old-time collaborator, Naina Bhaval, and Malay Nayak, who actually has helped us with the integrals, I must say that, because we tried to get the integrals in spinor basis for molecules. That was not very easy. For atoms, a lot of people are working like Bhanu Das and many other people, but molecule, not many people are working. Malay Nayak is one of the persons who actually helped us in the integrals. That was a very technical thing without which we can't write the codes. Using those integrals, we have to rewrite many codes because all the symmetries, so please try to understand it is not running the black box because all the symmetries are gone. So the people had written the code, Kaushik is one, but it was started by Sudip Sasmal and Himadri Pathak. I must mention them that they really worked very hard to write codes. And you know, code writing is so difficult, they actually did for 2 to 3 years, just silently working without publishing. And I'm very thankful to them because these days it's very hard to get students who will work on a code for 3 years without publishing. So thank you very much for your attention. This is just the registration page of the NPTEL Plus workshop in case anybody is interested. Thank you.
Thank you.
Swayam Prabha, Digital India, Educated India.